Welcome to Lesson 30, Introduction to Power Series Solutions of Ordinary Differential Equations. Our goals for this lesson are to use a power series to solve an ordinary differential equation and also an initial value problem. As a check of our initial value problem solution, the power series solution, let's use Euler's numerical method to find a numerical solution to the same initial value problem, and we can graph the two, the power series solution and the numerical solution, and then we will compare the two solutions. How does the number of terms we use in the power series, since we can only approximate an infinite series for the finite number of terms, how does limiting the number of terms used to approximate the power series affect its accuracy? So let's consider first a review of infinite series. This will be a prelude to our review, a very sketchy review of power series. If we have an infinite series, sum k goes from 0 to infinity of a sub k, this formally represents the infinite sum a naught, which is what we get when we substitute k equals 0 into here, plus a1, which would be the k equals 1 term here, plus a2, plus a3, plus a sub 4, plus a sub 5, and so forth. It has an infinite number of terms, and it is called an infinite series. So how do we sum an infinite number of terms like this? Sometimes we can find the sum of an infinite number of terms, sometimes we cannot. It depends on how large the terms in this infinite series are in the long run. Do they get very small after a while or not? So let's talk about the partial sums of an infinite series. The infinite series, the sum k goes from 0 to infinity of the a sub k's. Each a sub k is a number. Let's let s sub n be similar to what we have up here, but just go from k equals 0 to n of a sub k. So this represents a naught plus a sub 1 plus a sub 2 plus all the way through a sub n. There are what, n plus 1 terms here? That's a finite number of terms. We know how to add up a finite number of terms. We learned how to do that perhaps in the first grade. So at least theoretically, we can calculate s naught, s sub 1, s sub 2, s sub 3, s sub 4, and so forth. The zeroth partial sum, the first partial sum, the second partial sum, the third, the fourth partial sum, and so forth, just by changing the n in this formula over here. Suppose when we look at the limit as n goes to infinity of the s sub n's, that equals some finite number s. In that case, we can say that this infinite series converges to s, or this infinite series equals s. If this limit does not exist, the limit of the partial sums does not exist, we'll then say that infinite series diverges, or we can say that infinite series is undefined. For instance, if we had an infinite series that was just 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, all of the terms equaling 1, then this limit here would not exist. As you go off to n equals and goes, as n approaches infinity, these s sub n's would grow without bounds. They would not approach some finite number in the limit, and so we would not get a value for the infinite series 1 plus 1 plus 1 plus 1 plus 1 plus 1, and so on. So let's look at a particular type of an infinite series called a power series. Something like this. The sum where k goes from 0 to infinity, c sub k, x to the k. C sub k's here in this are some numbers, and we have a variable basically raised to the kth power. So the first term here is c naught times x to the 0 power, which is just going to be c naught. When k equals 1, we'll get c sub 1 x to the first power, which is just going to be c sub 1 times x. So what we're going to do then is pick some real number x, and we'll still look at a partial sum. S sub n, which is going to depend on the value of x in this case, is going to be the sum k equals 0 to n, because we're looking at an nth partial sum here, c sub k x to the k. And that, if we write it out, is c naught plus c1x plus c2x squared plus all the way through cn x to the n. Let's talk about this c naught term for a minute. Where did it come from here? It came from k being 0, didn't it? And we would have here c sub 0, which is c naught, times x to the 0. Well, if x is not 0, then x to the 0 is 1. And so this would just be c naught times 1, which is c naught. But the slight fly in the ointment is, what happens if x equals 0? In that case, the 0th term here, the k equals 0 term, is going to be c times c sub 0 times 0 raised to the 0 power. When we talk about power series, we're going to make the assumption that for all values of x, when k equals 0, this k equals 0 term is just the constant c naught. We're not going to get into arguments about 0 to the 0 being undefined. You can think of this as being the definition of this partial sum, where the 0th term just gives us c naught, no matter what the value of x is. Well, we know how to add up a finite number of terms, so we can find the 0th partial sum, the first partial sum, the second, the third, the fourth partial sum, and so forth. And then we just do the same thing as we did earlier. Suppose that for that particular value of x, this limit of the nth partial sum of x converges to some number. Let's call that number s of x. In that case, we can say that this power series converges to s of x, or we can say this power series equals s of x. If that limit of the s sub n of x's, the partial sums, does not exist as n goes to infinity for that value of x, then we'll say that that infinite series diverges or is undefined for that value of x. Let's continue talking about this power series. The sum k goes from 0 to infinity of c sub k x to the k. This power series may converge for some values of x and diverge for some other values of x. The interval of x values where this series converges is called the interval of convergence of that series, or for that series. Our present goal is to find solutions of the differential equation involving y of x in the form y of x is this infinite series. We'll do that in this lesson. In this lesson, we have x to the k here, the sum of the c sub k x to the k's. In the next lesson, we'll look at power series of this form as possible solutions. The sum k goes from 0 to infinity, c sub k x minus a, that quantity, raised to the k power. This is called a power series centered at a. In a later lesson, much later lesson I guess, we will look for solutions of some ordinary differential equations that involve infinite series that are not quite power series. We'll be looking at what's called the method of Frobenius. And what we'll look at is for solutions of the form y equals x to some number r times a power series, or y equals x minus a raised to the r times a power series. And in this cases, this r, in the cases we're going to look at, is not going to be a positive integer. It'll be some other type of number, and so it will give us solutions that we would not get if we only considered power series of the two forms that we have here. So this method of Frobenius will allow us to solve more ordinary differential equations than we could otherwise. In this lesson, we're going to consider the following initial value problem. Here's the differential equation, y double prime plus 2xy prime minus x squared y equals 0. This is a linear homogeneous differential equation. The initial conditions are y of 0 equals 2, y prime of 0 equals minus 1. So we'd like to solve this initial value problem. And also, if we just look at this differential equation at the top by itself, we would also like to find all solutions to just this differential equation. In other words, we would like to find its general solution. Let's talk about a general fact concerning this homogeneous linear differential equation. Y double prime, the second derivative of y with respect to x, in other words, plus p of x times the first derivative of y plus q of x times y equals the zero function. Let's look at this initial value problem for this fact. We have that differential equation, homogeneous and linear. We're going to require a solution to satisfy two initial conditions. Y of a number a is some number y naught, and y prime at the number a is equal to y sub 1. Now here's what we can say. If we look at this equation, we notice that there are two functions of x here, p of x and q of x, explicitly in this differential equation. If p of x and q of x are both continuous at that number a that we see right here, then there is an open interval I containing the number a such that the initial value problem has a unique solution on I. Coming back to this initial value problem, remember that we would look at this equation as y double prime plus p of x y prime plus q of x y equals 0. So in this case, the p of x function is 2x. The q of x function is minus x squared. Both p of x and q of x are continuous on minus infinity to infinity. And that tells us that considering these initial conditions happen at x equals 0, this initial value problem has a unique solution near x equals 0, and maybe elsewhere also. So we're going to look at convergence of power series solutions. So we're going to consider this second order linear homogeneous differential equation, homogeneous since we have 0 on the right, and we're going to look for solutions that may be centered at, that may be power series centered at x naught. So y of x will be the sum, k goes from 0 to infinity, c sub k, x minus x naught to the k. So this infinite series represents c naught plus c1 times x minus x naught plus c2 times x minus x naught squared. Next term would be c3 times x minus x naught cubed, and so on. Here's a fact. Let's suppose that p of x has a power series representation. It's a power series, once again, centered at x naught. and these coefficients I'll call a sub k. They're not necessarily the same as those c sub k's, obviously. And suppose that this converges for all x satisfying x minus x naught is less than, an absolute value is less than R1. And suppose we have a power series for q of x also. The sum k goes from 0 to infinity, b sub k, x minus x naught to the k. And this is equal, this series converges to q of x for all x satisfying x minus x naught is less than R2. Let's let R naught be the minimum of this R1 and R2. Then we conclude in this fact that we can write y of x is the sum of some c sub k's, x minus x naught to the k's, and this power series will converge for all x satisfying x minus x naught is less than R naught, R naught being the minimum of those two r's that we found earlier. Now, R1 and R2 might be the radiuses of convergence, the radii of convergence of the p of x and q of x series. And what this says then, if you take that minimum of the two radiuses of convergence, this power series will converge in an interval having that minimum radius of convergence, R naught being the minimum of R1 and R2. So let's see how we can substitute a power series y of x equals sum k goes from 0 to infinity, c sub k, x to the k, into an ordinary differential equation and solve for the coefficients. So let's look at this problem right here. Y double prime plus 2xy prime minus x squared y equals 0. First of all, let's look at y double prime. If we just differentiate this series up here for y of x term by term, differentiate it twice, we'll get that y double prime of x is the sum k equals 2 to infinity, k times k minus 1, c sub k times x to the k minus 2. You might say, well, don't we have to start with k equals 0 down here? Well, if k equals 0, this term will be 0 since it has a factor of k, 0 right here. If k equals 1, then this factor k minus 1 in this term is 0. And so the first non-zero term starts at k equals 2, possibly non-zero term. So now let's re-index this. Let's, instead of going from 2 to infinity, let's go from 0 to infinity and add 2 to all the k's here. So we'll get a k plus 2 times k plus 1, c sub k plus 2, x to the k. K minus 2 plus 2 is k. Now, I'd like to get some terms plus a sum of something times the x of k's, k going from 2 to infinity. So if I look at this sum right here, the 0th term, k equals 0, turns out to be 2c2. The k equals 1 term here turns out to be 6c sub 3x. And then we have all the rest of the terms starting at 2 going to infinity. Let's move on to 2x times y prime. Well, 2x times y prime of x is 2x times the sum where k goes from 1 to infinity, k c sub k, x to the k minus 1 power. Once again, we could ask, why don't we start with k equals 0 here? Well, we could, but this factor of k here being 0 would make that term equal to 0. Okay, so bringing that factor of 2 times x inside using the distributive law, we can write that expression here as the sum where k equals 1 to infinity, 2k c sub k, x to the k. Now this starts with 1. So let's put the k equal 1 term out front, and that turns out to be 2 times 1 times c sub 1 x to the first power, which is this, 2c sub 1x, plus the rest of the terms. Sum k goes from 2 to infinity, 2k c sub k x to the k. Let's look at this term, minus x squared y. X squared y is equal to the sum k goes from 0 to infinity, c sub k x to the k plus 2, because we're just multiplying each of these terms up here by an x squared. That gives us an x to the k plus 2 instead of an x to the k. And then once again, let's re-index this, and we'll get these terms over here. Continuing our calculation, let's look at y double prime plus 2xy prime minus x squared y. Well, y double prime we saw was equal to this sum. 2xy prime is equal to this sum in blue. Minus x squared y, well, that's this stuff right here. Minus k equals 2 to infinity, c sub k minus 2 x to the k. Now, let's do a little bit of manipulation on all of this stuff. On this first sum, the k equals 0 term is going to be 2 times 1 times c sub 2 times x to the 0. And so that is just 2 times c sub 2. When k equals 1, this will be 3 times 2 times c sub 3 times x to the first power. That is 6c sub 3 times x. So these two terms are the k equals 0 and k equal 1 terms from this series. The rest of the terms we'll just write down right here. K equals 2, the sum k equals 2 to infinity of that sort of stuff. Now, on this next summation, let's pull out the k equals 1 term. That'll be 2 times 1 times c sub 1 times x to the 1. So that's 2 times c sub 1 times x that we see down here. And then the rest of the terms in this sum will be the sum of these things, k going from 2 to infinity. This one we'll leave alone. Now, why did we do this? It's because now we have a sum involving k equals 2 to infinity and an x to the k here. Here we have a sum k equals 2 to infinity, x to the k here. And here, sum k equals 2 to infinity and an x to the k here. These three sums in red, blue, and black can be combined into one sum. So that's what's going to happen at the next step. These first three things that we see right here are just these two terms plus this term. And then to combine this sum, and this sum, we get this stuff right here. The sum k equals 2 to infinity times this stuff basically, k plus 2 times k plus 1 times c sub k plus 2 x to the k, plus this stuff right here, 2k c sub k x to the k, minus this stuff here, c sub k minus 2 x to the k. All of this stuff summed k equals 2 to infinity. Now we can simplify this one more step. Each of these three terms here has a factor of x to the k. And we can factor that out. So finally, we get that this stuff up here equals this stuff down here. First of all, we have these three terms that we see here. And now, factoring an x to the k out of this, we have inside the parentheses here 3 things added together and that common x to the k factor outside. So this differential equation, y double prime plus 2xy prime minus x squared y equals 0, can be written as this stuff plus the sum of this stuff equals 0. So continuing with this, if y of x is the sum k equals 0 to infinity c sub k times x to the k power, then what we need to solve is that this stuff equals 0. We saw this on the previous slide. Now, if we look at this for a minute, here we have a constant term. These two terms have a factor of x in them. So let's rewrite all of this stuff right here as 2c2, this term, plus 6c3 plus 2c1, that quantity times x, which takes care of these terms. And then the rest of this will just be copied down. Sum k equals 2 to infinity of all of this stuff again. Now, if this equals 0 for all x, in other words, if this is the 0 function, because we want this differential expression to equal the 0 function, all of the coefficients of the powers of x must be 0. So this constant term has to be 0. 2c2 equals 0, so c sub 2 equals 0. The coefficient of x, this stuff right here, has to be 0. 6c3 plus 2c1 equals 0. Solving that, we get c sub 3 equals minus 1/3 c sub 1. All of the higher power of x terms, the coefficients have to be 0 too. So that means that for each k here, k being 2 or greater, this coefficient has to be 0. So if this is just the sum of 0 times x to the k. So that means k plus 2 times k plus 1 times c sub k plus 2 plus 2 times k times c sub k minus c sub k minus 2 equals 0. That just says that this coefficient right here of x to the k has to equal 0. Now, just a little bit of algebra can be used to solve this equation for c sub k plus 2 in terms of c sub k and c sub k minus 2. And if we do that, we get c sub k plus 2 is 1 over this stuff, k plus 2, k plus 1, times the quantity c sub k minus 2 minus 2k c sub k. And this holds for k greater than or equal to 2. This is our recurrence relation to find c sub k plus 2 in terms of other values of the c coefficients. Still looking at that same ordinary differential equation and still looking at solutions of this form, a power series. So far we have found that c sub 2 is 0 and c sub 3 is minus 1/3 c sub 1. And c sub k plus 2 was this fraction times c sub k minus 2 minus 2k c sub k for k greater than or equal to 2. If you look at this, this tells us what C2, C3, C4, C5, C6, C7, and so on are, but C0 and C1 could have had any values when we just have these restrictions on the c's that come from this proposed solution to the differential equation. So the values of C0 and C1 could be any two values, and those two values will determine the rest of the C sub k for k greater than or equal to 2. And this happened because this ordinary differential equation we had up here is second order linear homogeneous. So what happens is if we take two slightly different choices of C0 and C1, we will get two linearly independent solutions to the differential equation. Both of those solutions will be power series. So we can use sage math to calculate two linearly independent solutions to the ordinary differential equation. We found out excuse me, before that we can let C naught and C sub 1 equal anything. And so what we'll do is pick two different choices for those two coefficients. So for y sub 1, let's let C naught equal 0, C sub 1 equal 1, and C sub 2 equals 0. We found out that C sub 2 in any solution had to have the value 0. But what about C sub 3? We found this relationship. C sub 3 is minus 1/3 C sub 1. We're going to use that when we come down here. So to compute y1, we'll let C be the list with the numbers 0, 1, and 0 in it. That's the C0 value, the C1 value, and the C2 value. And then we'll compute minus 1/3 times C sub 1, this stuff right here, and we'll append that to our list which we called C. So let's recall what's going to happen here. This 0 is C0. This 1 is C sub 1. This 0 right here is C sub 2. And this will compute C sub 3 and add it to this list. Okay, and now we want to append more coefficients, the C coefficients for our power series. And to do that, we'll use this recurrence relation. So we'll have C dot append, and then 1 over k plus 1 times k plus 2 times C sub k minus 2 minus 2 times C sub k. That's just using this formula here. And we're doing it for k starting at 2. And at this stage, we're going to only go out to k equals 7. We just want a few terms of this series. And then after this loop finishes, after all this code up here finishes, we will issue the command show C, and this is the list that we have. These are the coefficients, remember, of C0, C1, C2, C sub 3, C sub 4, C sub 5, C sub 6, and so forth. So y sub 1 of x is going to be a power series with these coefficients. So we have 0 plus 1 times x, which is this, plus 0x squared, minus 1/3 x cubed, which is what we have right here, plus 0x to the 4th, plus 1/12 x to the 4th, or sorry, 5th, yeah, for 5th, 0, 1, 2, 3, 4, 5, 1/12 x to the 5th, and it keeps on going forever. And here we can see a few more terms in this list if we wanted to write out more terms. Okay, let's compute over here y sub 2 similarly. Let's let C not be 1, C1 equals 0, more or less the opposite of what we had up here. And then C sub 2 will turn out to be 0. C sub 2 is always 0. Sorry about that. So once again, we'll start by initializing a list of values and assigning it to C. And those values are going to be up here, 1, 0, and 0. And then once again, to find C sub 3, we use this formula, minus 1/3 C sub 1 equals C sub 3. And so once again, to the C list, we append minus 1/3 times C sub 1. After that, we once again, by this for loop, use this recursive formula to find more of the C sub k's. And finally, after this for loop is finished executing, we will show the resulting list of C values. 1, 0, 0, 0, 1/12, 0, minus 1 over 180, 0, and so forth. So what this y sub 2 turns out to be then is 1 plus 1/12 x to the 4th minus 1 over 180 x to the 6th plus more terms ad infinitum. So we have found two linearly independent solutions to that ordinary differential equation, which was what? Y double prime plus 2x y prime minus x squared y equals 0. We have seen two linearly independent solutions to this differential equation up here, and the general solution just to this differential equation would be an arbitrary linear combination of what we called y sub 1 of x and y sub 2 of x. But now we're going to consider the entire initial value problem, the differential equation plus initial conditions. Y of 0 equals 2, y prime of 0 equals minus 1. Well, just from this differential equation, we saw that C2 had to be 0, and C sub 3 was minus 1/3 C sub 1. And so, and we also had a recurrence relation. C sub k plus 2 was given by this stuff for k greater than or equal to 2. Let's just see what happens if k equals 2. This will be C sub 2 plus 2. C sub 4 is going to equal something involving what? C sub 2 and C naught, which remember don't have values here yet, do they? But let's see what happens. If we let y of x equal this infinite series, this power series that we had before, what is y naught? Well, it's c naught plus c1 times 0 plus c2 times 0 squared plus c3 times 0 cubed, and so forth. All of these terms are 0 except for the c naught term. So y of 0 is equal to c naught, and we also know that by our initial value problem, we're looking for a solution where y of 0 is 2. So y of 0 has to be 2, and that tells us that for this initial value problem, c naught has to be 2. Now, we have a condition on y prime also. So differentiate this, we get y prime of x is c1 plus 2c2x plus 3c3x squared, and so forth. Plug in a 0 for the x's, and we get c1. This term will be 0. This term will be 0, the next one will be 0, and so on. And so y prime of 0 is just c1. But according to our initial condition up here, y prime of 0 has to be minus 1. So y prime of 0 also equals minus 1, and that forces c sub 1 to equal minus 1. So what have we noticed? These two initial conditions give us the values of c naught and c1. any function that satisfies this initial value problem has to have c0 equal to 2 and c1 equal to minus 1. And once these two are determined, then c sub 3 is determined by this equation, c sub 4 and further c sub k's are determined by this relationship, and so we end up getting a unique solution to this initial value problem. So let's look at a Python program to find the coefficients of the power series, the solution to that initial value problem, and plot the series solution using the first 13 terms of that power series. This program over here consists of a main program down here, and we also have a function f defined here, and f is basically going to be defined to be the power series representing the solution, but only using 13 terms. We also are going to import something, and once this program is executed, it will produce this output that we see over here. So let's see what's going on. Perhaps we should start in the main program. First of all, the number of coefficients that I want to use is 13. And I'll start off by letting C, the list of coefficients of the powers of x, be 2, minus 1, 0, and 1/3. Let's remember that we're looking for a solution y of x such that y of 0 is 2, y prime of 0 is minus 1. We saw that for any solution to the ordinary differential equation, the C2 coefficient, the C2 number, had to be 0, and the C3 number has to be minus 1/3 the C1 number. Minus 1/3 times minus 1 is 1/3. And now we'll calculate using the recurrence formula all of the rest of the coefficients through the 13th. So for k in range, starting at 2, going to the number of coefficients that we want, which is 13, we will use the recursion formula to calculate the next c sub k plus 2 basically, and we'll append it to the list C. There's a print C statement in here to print out the list, but in this case I didn't show the output of that. And now, once we have everything we need coefficient-wise in this list C, we can start getting ready to plot the graph. I'm going to, in the rest of this program, look at two lists, X list and Y list. When this code down here executes, X list will fill up with values of X that are in this graph. So X list is going to be a list of some of the values of X, and they're somewhere on this horizontal axis. The Y list is also starting out to be empty, but I will fill it up with Y values. In fact, I will fill it up, the X list and Y list, with values that correspond to ordered pairs of numbers for points on this graph. So the number of points that I'm going to graph are 50. Between 0 and 2, I'm going to look at 50 discrete values of X. The delta X, then, the distance between one of the X values and the next X value that is graphed, is just going to be 2, the length of this interval, I'm plotting everything for x between 0 and 2, divided by the number of points. Number of points is 50, so delta x is 2/50ths. Okay, so now here's the for loop. For k in the range of num points, so this is basically going to let k be 0, 1, 2, 3, all the way through num points minus 1. X is going to be 0, where we start from, plus k times the delta x. So the first one is going to be when k equals 0, and so this x value is going to be 0 plus 0 times delta x, so x equals 0. Next time through, when k equals 1, we'll have x equals 0 plus 1 times delta x. So wherever 1 times delta x is, that's the next x value for a point on the graph that's plotted. The next x value is 2 times delta x, 3 times delta x, 4 times delta x, and so forth, since all of the x values are the form 0 plus k times delta x. Okay, I'll append this value that we just found to the x list. Then we will compute y equals f of x for that power series representation, at least the first 13 terms of the power series. In order to compute f of x, I also have to pass this Python function c, the list of coefficients, and the number of coefficients that I am using in the computation. F is defined up here. We'll look at it in a minute. Once we compute a value of y, we add that value of y to ylist. Ylist dot append y. After this loop is finished, I have xlist values in xlist, and I also have values in ylist, and I want to plot xlist versus ylist to get this curve. To do that, we have the following up here. Import matplotlib or lib.pyplot as plt. So from that library plt, I will use the function plot, and I'll plot the x values versus the y values, and it gives us this curve. What happens is the x-list and y-list are discrete. They're just certain points along this curve. When you use this plot, it will link or plot line segments between two different points on this curve that come from this list. Okay, so this is really, you can't see it because there are 50 little line segments making up what looks like this smooth curve. Now, let's look at the definition of our function f. I pass f a value of x, and f is going to return a y value. I'm going to pass it a list of c values, which I'll call little c here, and I'll also pass it the number of coefficients. And here's what will happen. We have just a little bit of code here for computing that series. First sum will equal 0, and then for n in the range of numcoefs, which will go from 0 to num coefficients minus 1 basically, we'll add to this sum the value of c sub n times x raised to the n power. And so we go through this loop basically 13 times, adding up a partial sum for that infinite series. And then once it's done that, we return the sum to the main program where this function was called. Well, let's see, where was this function called? Let's just look down here for a second and see if we can find it. It's right here, okay? And let's see, we In the main program, we pass it the value of x, and so it's passed to this first parameter up here, which is called x. The next thing we do is pass it that list of c values, and I called it in the main program capital C. Notice that capital C equals this stuff, capital C dot append this stuff, and so forth. So I'm passing it the variable capital C into the variable little c. That's okay. The names don't matter. It's the position in the parameter lists that makes the difference. And the other thing we pass to this function f is num underline coefficients, but in the function over here, I gave that a different name, just slightly different also, num coefs without that underline symbol. And so everything, the parameters that we have down here, how many parameters do we have? 1, 2, 3 are passed to the parameters up here, 1, 2, and 3. Sometimes these parameters in the function, this list of parameters is called a formal parameter list. The one down here is often called the actual parameter list. Other people might call it something else, but that used to be some common nomenclature. So anyhow, when we plot this curve by running this program, we get a curve that looks something like this. So at this point, this is what we think the graph of the solution to that initial value problem should look like. Let's see if it really does. Is the solution that we got reasonable? Is it fairly accurate? We would like to know the answers to those questions. So what we want to do now is use Euler's method to determine if this solution, this proposed solution we got, looks reasonable for the initial value problem we were considering. The Euler's method is based on the tangent line approximation that hopefully you saw in a calculus course, and we will generalize this tangent line approximation to work on a system of first order ordinary differential equations. So let's start with the approximation to the first derivative. If h is a small number, then f prime of x, the derivative of f at x, is approximately equal to f of x plus h minus f of x over h. For differentiable functions, this approximation gets better as h gets smaller. If we rearrange the terms in this, we can get, by just a little bit of algebra, f of x plus h is approximately equal to f of x plus f prime of x times h. Let's replace the f of x's by y instead. Y will be our function of x. So I'll next write y of x plus h is approximately equal to y of x plus y prime of x times h. Next thing we'll do is a discrete approximation of this formula. So we're going to think of an interval on the x-axis evenly divided into subintervals with endpoints x naught, x sub 1, x sub 2, x sub 3, all the way through x sub n. The distance between two adjacent x sub i's, that distance is h. So we'll let x sub k plus 1 equal x sub k plus h. For instance, down here, x sub 2 is equal to x sub 1 plus h. X sub 3 is equal to x sub 2 plus h, and so on. Let's let y sub k plus h equal the following. Y sub k plus the derivative of y with respect to x evaluated at x sub k times h. In that case, y sub k plus 1 is a discrete approximation to our function y evaluated at x sub k plus 1. A picture to indicate that is the following. Here's in blue, function y equals f of x, and right here is the point x sub k, y sub k, and this is a point of tangency for this straight line down here. Okay, so if we go from, let's say, x sub k over to x sub k plus 1, a distance h, this point on the tangent line, which has x coordinate x sub k plus 1, is going to have y coordinate y sub k plus 1. So on this tangent line, this is the point x sub k, y sub k, and also on the tangent line is this point right here, x sub k plus 1, y sub k plus 1. If h is small, this point should, on the tangent line, this point on the tangent line should be pretty close to this point on the curve corresponding to that same x value. As you let h get bigger, then these two might diverge quite a bit, but we're only interested in this approximation for quite small values of h. Let's use a numerical method, Euler's method, to approximate the solution to the initial value problem that we have been considering. So I have a second order linear homogeneous differential equation up here. Euler's method allows us in generality to solve lots of different types of initial value problems, not necessarily a linear one like we have here. So here's what we'll do. I want to change this to a system. I want to look at this second order differential equation up here, and I want to change it to a system of first order differential equations. And so I'm going to more or less introduce some new functions. Y is a function of x, let's remember. So the first thing I'm going to do is I'm going to let y and w be the same function. Let w equal y. W here is a function of x also. I'm going to let z be the derivative of y with respect to x. Okay, well, not too much there. We've just introduced a couple more variables, or actually functions, into this. But looking at these two, we can see now that the derivative of w with respect to x is just z. If I differentiate, why is this true? If I differentiate both sides of this equation, the derivative of w with respect to x equals the derivative of y with respect to x. But wait a minute, the derivative of y with respect to x equals z. So putting those two together, we get that the derivative of w is equal to z. But we can also say the following. If I look at the derivative of z with respect to x, what happens, looking up here, if I differentiate z with respect to x? The derivative of z with respect to x is going to be the second derivative of y with respect to x. And that's exactly what we have here. So these two equations come from introducing w and z as we did up here. But wait a minute, I now have basically two equations up here. So if I look at y double prime equals 2xy prime plus x squared y, Oh, and that should be a minus x squared y. Oh, sorry, it's correct, isn't it? If I subtract these two terms from both sides of the equation, that'll leave y double prime on this side, and on the other side we'll have minus 2xy plus x squared y. So actually this is okay. No sign error. So what can I say? Well, the first thing I know is that the derivative of w with respect to x is z. That's what we showed right up here. And let's see what this one is. The derivative of z with respect to x, well, wait a minute, that's the second derivative of y with respect to x, isn't it? Which is what I have right here. And now let's look at the other side, x squared times w. Now, w is y, so this is just x squared y, this stuff right here. Then I have minus 2xz, but z was y prime. So 2xz is 2x y prime. There's a minus sign here, minus sign there too. So what happened is this equation right here is just basically the second derivative of y with respect to x equals x squared y minus 2x y prime. Now why did I do this? What is going on here? If you look at these equations, on the left-hand side of these two equations, I have the derivative of w with respect to x and the derivative of z with respect to x. On the right-hand side of these equations, we don't see any derivatives at all. What we see are z's and w's, and also x occurs, which was more or less the independent variable that we started with in our initial value problem. So just single first order derivatives on the left, no derivatives on the right, just kind of algebraic expressions on the right. Well, that's nice because there are ways to solve systems of first order differential equations when they have those characteristics. So Euler's method basically can be called a tangent line approximation. We're going to pick a small positive value of h, so h will be greater than 0. At the initial conditions, they're given when x is equal to 0, right? So I'm going to let x not equal 0. W is the same as y, so the y naught value is going to be 2. And remember that z is the derivative of y with respect to x. The derivative of y with respect to x at 0 is minus 1, so we'll let z naught equal minus 1. Now, in a loop, we'll do the following. We already have x naught defined, so we'll let x of k plus 1 equal x of k plus h. So in a loop, I'm going to find x sub 1 in terms of x sub naught, x sub 2 in terms of x sub 1, and so forth by adding successively h's to the previous value of x. And these can be stored in a list. Now, we know that the tangent line approximation can be written this way. The k plus first value of w is equal to the kth value of w plus h times the derivative of w with respect to x. And now wait a minute, the derivative of w with respect to x is just z. And so w sub k plus 1 equals w sub k plus h times z. On the other hand, z sub k plus 1 is going to be z sub k plus h times the derivative of z with respect to x. And so we get x sub k plus h. And now what was the derivative of z with respect to x? It was this stuff right here. The derivative of z with respect to x equals x squared w minus 2xz. And that's what we have here. for this derivative. Now, we can do that in a program, and this one, once again, is going to use Python. I'm going to import matplotlib.pyplot as PLT. Then we'll create 3 arrays. W will have the element 2 in it, number 2 in it. Z will have number -1 in it. X will be 0. And for this program, the increment h that I'm going to use is going to be 0.01. So I want to graph this approximate solution for x between 0 and 2. Well, if h is 100th, then I'm going to need to use this increment about 200 times to get x values between 0 and 2. So for k in range 200, which actually means that the k values will go from 0 through 199, I'm going to calculate the x sub k plus value, k plus 1 value, and put it in the list. X dot append x of k plus h. Remember down here somewhere, here it is right here, x of k plus 1 equals x of k plus h. I'm going to start making a W list too. W dot append W sub k plus h times E sub k, which is what we have more or less right here. Z dot append, and then we'll have this appended to that. Z sub k plus h times the quantity x sub k squared times w sub k minus 2 times x sub k times e sub k, which is what we have right up here. And then after this loop is finished, we plot x versus w. Remember that w is y. So we're basically plotting x versus y here, our solution to the initial value problem. This, remember, is called Euler's method, and it can be found in many elementary books, both on differential equations or numerical analysis. So here is the program that we just went through, and when we run it, this is the graph that we get. Well, if your memory is at least as good as mine, this does not look like the graph that we got from our power series solution. What is going on? If your memory is not as good as mine, let me refresh it for you. This is what we got using 13 terms from our power series. And over here, this is the graph that we got for the solution to the initial value problem using Euler's method. Unless you have cataracts, these two curves probably do not appear to be the same. So the question is, if both of these are supposedly solutions to the initial value problem, what went wrong? Remember that those initial value problems of the type that we're looking at should have unique solutions. So it could not have two different solutions, one looking like this, one looking like that. Instead of using the first 13 terms in the power series, let's plot using the first 20 terms. Here is the program for doing that. It's almost identical to the one that we saw where the number of points was, number of coefficients was 13. The change in this program is just I believe, this one statement right here. Num underline coefs equals 20. When we run this program, here is the curve that we get. It looks virtually identical to the one that we got using the Euler method. So the next thing we could ask is, well, letting the number of coefficients or the number of terms used from the power series equaling 20 gave us a graph that looked like the numerical solution, Euler's method solution. What happens if we increase and look at more terms? If you let the number of coefficients equals 30, it makes virtually no difference to this curve. You might like to try that yourself sometime. But in any case, it looks to me like 20 terms are good enough for our purposes, at least if you want the graph of the solution between x equals 0 and x equals 2. Just in case you don't have a photographic memory, let's look at the two curves next to each other. This one over here is the power series solution using 20 terms, and over here is the graph of what we got using Euler's method with an increment of 0.01. If you look at this one starts at 0, 2, and it goes down, and the minimum is, well, kind of hard to tell, but close to 1, I guess. In this one, Euler's method, it starts about at 2 again, and it goes down and it has its minimum maybe just a little bit to the right of 1. Is this one slightly to the right of 1 also? Kind of hard to tell. This one might have a slight difference here. And then they both go up to about 2, 2, don't they? This point looks like it's about 2, 2 also. So there might be just a little bit of difference in these two curves by looking at where the minimums occur here, but they are very close. What we have to remember is that neither one of these is the graph of the exact solution to that differential equation, that initial value problem. This one was a power series approximation, and this one, Euler's method, was a tangent line approximation. If you use small values of h here, and if you use a large value of terms in the power series over here to do our approximations, these two curves should be pretty close. Now, one thing to, well, first of all, let's make a conclusion. We saw that when we used 13 terms from the power series, that did not give us graphs that looked anything like these two. We needed, in our power series solution, to use more than 13 terms from the power series to get accuracy that we can be happy with. One question that we could ask is, well, how many terms would we need to get a certain level of accuracy? That could be a fairly hard question to answer in general for power series because we don't really have a nice formula for the C sub k's. What we have instead is a recurrence formula. So if we wanted to derive some inequalities to tell us how close these solutions are, it would probably require a lot of work, which we're not going to do today. But in any case, we can see at least that 13 terms were not enough. 20 terms were about enough to get a solution that was fairly accurate. So, in this lesson, what did we learn? We could find power series for y prime of x and y double prime of x, the first and second derivatives of y, by differentiating the power series for y of x term by term. We use this fact to substitute these into the ordinary differential equation and solve for the coefficients in the power series solution. we got recurrence relations that told us what some of the c's were in terms of prior c values, the coefficients. We found what the coefficients had to be in order to satisfy the initial value problem, and then to check to see if everything worked right, we used Euler's method, a tangent line approximation, to find a numerical solution to the same initial value problem, and then comparing the graphs of the analytic solution with the numeric solution, we compared them and found out that we didn't have enough terms in the power series solution. We used a partial sum to approximate the solution, and we didn't use enough terms in the partial sum to start with. We needed more terms to get an accurate representation of the solution. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.